Okay, I'm going to leave you there, and in the next video, we're actually going to look at the enzyme that makes G-serine, and it's called serine racemase. And in general, what racemases are is they're enzymes that reversibly convert the G and L amino acids. Okay, and in fact, although it's not an amino acid, we've actually encountered one racemase before, and that was methylmalonyl-CoA epimerase. Okay, that's often named methylmalonyl-CoA racemase. Okay. And if you think about what racemase means, okay, racemase, what did you have when you had a racemic mixture? Well, when you had a racemic mixture, that meant you had a mixture of D and L isomers, 50-50%, right? You get 50% D, 50% L. That's a racemic mixture, right? So that's where this enzyme gets its name from. That it's racemizing the isomers into the other isomers. In other words, it's taking D isomers and converting them into L, or the reverse reaction is taking L and converting them into D. And ordinarily, when we consider racemases to be in humans, we're considering the process of going from L-serine to G-serine. And I'll leave you there. In the next video, we'll actually talk about racemases and their implications in humans. See you in the next video. Welcome back to the playlist on amino acid metabolism. We've already seen a few catabolic pathways for various amino acids, but we're really going to get into the actual meat of the pathways now. Okay, and specifically in this video, we're going to look at the catabolic pathways for threonine, glycine, and serine. This picture that you note here on the left also has tryptophan, alanine, and cysteine, but we're going to get those in a different video. Okay, and in fact, we're going to do that in multiple videos. Okay, now what I want to have you bear in mind is several things. Number one, these 6 amino acids, which are threonine, glycine, serine, tryptophan, alanine, and cysteine, all 6 of these amino acids are going to integrate into pyruvate. Okay, and for that reason, and we'll talk about why this is in a few minutes, if you integrate into pyruvate, that implies that you are a glucogenic amino acid. Or in other words, you can say that the catabolic pathway for your amino acid is glucogenic. Well, there are 2 kinds of products that we can get through amino acid metabolism, and those are glucogenic products and ketogenic. When you say something ketogenic, what you're implying is that it gets degraded ultimately to either a ketone body or acetyl-CoA. If it's a ketone body, then that ketone body can just be released by the liver and put into the blood to fuel another tissue. If it's acetyl-CoA, then the acetyl-CoA will form ketone bodies, and then the ketone bodies get released. Okay, so keep in mind that all these processes that we're doing right now are occurring in the liver mostly. Okay, now if you're a glucogenic product, that implies that you either integrate it to pyruvate or some member of the latter part of the CCA cycle, which can ultimately be converted to oxaloacetate, and the oxaloacetate can enter gluconeogenesis. So if you're a glucogenic product, that means that you can form glucose. Acetyl-CoA in general will not be used to form glucose. Acetyl-CoA is purely a ketogenic product, meaning that acetyl-CoA is funneled into ketone body biosynthesis. Now the liver is doing these processes, right? So when the liver makes the glucose and it makes the ketone bodies, it dumps them into the blood, and then those products go throughout the blood to peripheral tissues and fuel them. Okay, so I just want to have us bear that in mind. In this video, what we're going to do is we're going to look at threonine, glycine, and serine metabolism. Okay, so our first enzyme is called threonine dehydrogenase. So we're going to kick it off with threonine. And our threonine has this hydroxyl group on it. And specifically, when we dehydrogenate it, we're going to get a ketone, or a carbonyl, right? We're going to get a carbonyl. And so, that carbonyl is preparing it for a nucleophilic acyl substitution. And of course, in the process of doing this reaction, we get NADH. So those electrons from threonine get funneled into a hydride that's now in the form of NADH. Okay? Now, what we've done in this reaction by dehydrogenating the hydroxyl group is we have this ketone now. I'll do this in blue. We have this ketone, right, or this carbonyl. And what we've done is we've prepared that molecule, 2-amino-3-ketoglutarate, for a nucleophilic acyl substitution. And it's going to do the substitution with coenzyme A. And so what we're effectively going to do is we're going to split this bond right here. Okay?